say that chemistry's my hustle, and your brain is like a muscle. So settle in because it's time to flex.
Good morning, everyone. I hope that you had a great weekend. Hopefully, at this point, you've got this either printed off or you have the notes somewhere in front of you with something to write on. Also, you're going to need a calculator because what we're getting into in this learning target is the ability to actually solve gas law problems. That's what 12.2 is all about. Remember that since this is on YouTube, you can speed up or slow down this video, and of course you can pause. So I'm going to move at a relatively quick pace because it's going to end up being a long video. But remember, you can come back to it and you can speed it up if I'm going too slow for you. So in the last learning target, we talked about qualitative relationships. Things like, as the temperature increases, the particles move faster, which results in more collisions, therefore a higher pressure. That would be a qualitative reasoning or explanation, but in sometimes we need actual calculations, which is what we're going to get into right now. The first part of 12.2 is 12.2a, which says, I know how to convert between temperatures, pressures, and volumes. In terms of I'll start from the easiest one. Volume conversions, usually you're given either liters or milliliters. So the one that's most common is going to be this conversion here, the liter to milliliter conversion. We've seen this before, so I'm not going to spend too much time on it, but we'll practice it. As far as temperature conversions, one really important conversion that you need to know is the ability to convert to and from Kelvin. Kelvin is a temperature that starts at 0. And we know that temperature is really a measure of how fast the particles are moving. Well, when the particles stop moving, that's 0 Kelvin. Kelvin is equal to, the easiest conversion is just taking whatever the temperature is in Celsius and adding 273 to it. If you do that, you've got your temperature in Kelvin. I've also provided two other equations here for calculating out Fahrenheit and Celsius from Fahrenheit. But the one to get to Kelvin is the one that's going to be the most important. And then we have our pressure conversions. Unfortunately, there are a lot of pressure units. That's just the reality. So we need lots of conversion factors. And probably this top line here is the one that's going to help the most. This allows you to convert between any one of these units: atmospheres, pascals, kilopascals, millimeters of mercury, and torr are all examples of pressure units. Okay, before we practice some pressure conversions, let's finish this conversation off with STP. What does STP stand for? Well, it's standard temperature and pressure. Standard temperature and pressure. And specifically, at standard temperature and pressure, the standard temperature is 273 Kelvin, and the pressure is 1 atmosphere. This is just one unit of pressure, and at STP, it's 1 atmosphere. Two numbers, values that you should remember. So what would that temperature be in Celsius? Well, our equation is right here. We know that temperature Kelvin equals temperature Celsius plus 273. So solving for temperature Celsius, our temperature Celsius will equal whatever temperature Kelvin is minus 273. And that would equal, so we have temperature Kelvin is 273 Kelvin at STP. If we subtract off 273, that equals 0 degrees Celsius. Okay, what would a standard pressure be in kilopascals at STP? Well, we know that at STP, the pressure is 1 atmosphere. I'm going to use a little trick here. You've seen this before. Remember when we were talking about conversions and converting things early on in the semester? We used some train tracks and we canceled our units out. Atmospheres cancels, and I'm going to convert to kilopascals. This requires that we know a conversion factor, and we do. Here's our atmospheres. It's equal to this many kilopascals. One atmosphere is 101.3 kilopascals. So that would give us that pressure at STP. How about, this is stating the same thing. All right, not a great question. So we basically just answered that. All right, moving on to page 2. Let's do a couple more examples. It says convert 25 degrees Celsius to Kelvin. 25 degrees Celsius plus 273 equals 298 Kelvin. How do I know that? Well, remember that temperature Celsius plus 273 equals temperature Kelvin. So that's why I did that. Next one. For any sort of pressure conversion, we're going to use train tracks. Can you find the conversion factor from atmospheres to millimeters mercury using the conversion factors that were given to you on page 1? You should have found that 1 atmosphere is equal to 760 millimeters of mercury. So if we multiply those two, we get a pressure equal to 1900 millimeters of mercury. And now for a volume conversion, we have 150.0 milliliters. Don't forget that 0.0 because, we're talking sig figs are still at play here. We're converting from milliliters to liters. Do you remember that conversion factor? For every 1 liter, there's 1,000 milliliters. So our answer is going to be 0.1500 liters. I did include those zeros because we want to maintain 4 sig figs in this one. Okay, so I've given you some practice problems on the bottom of page 2. These 4 temperature conversions. And on page 3, I've given you 5 more pressure conversions and 3 more volume conversions. Try those out yourself and I'll upload a key for these problems later. Now let's jump to our last topic of the day, and that is combined gas law on the top of page 4. Combined gas law. This is the combined gas law equation. It says that P1, which as you might have guessed is a pressure, times V1, which is a volume, divided by T1, which is a temperature, is equal to, let's say that we had some sort of system. Let's say that we had, at our initial phase here, we had some sort of container. And we had some particles moving around in it. And let's say we changed this container. So now maybe the volume had changed. And that might change the pressure or temperature inside. If we take pressure times volume over temperature, that equals the new pressure times volume over temperature. So the 1 versus the 2 is whether it's initial or final. Before we start plugging in numbers in the combined gas law, I want you to try solving for P2 and T2. P2, T2. And when I say that, I mean like isolate the variables, or in math you might isolate X. In this case, I want you to isolate P2 and T2. Go ahead and pause because I'm going to solve them out pretty quickly here. So hopefully you had a chance to solve for P2. P2, well, I'm going to do this one the long way here. Since P2 is located right here and we want to solve for it, in order to isolate it, we're going to have to get it by itself. And the only way to get it by itself, it's algebra. It's divided by T2. What do we have to do to get rid of the T2? We have to multiply it by T2 on both sides. And what do we have to do to get rid of the V2? Well, of course, we have to divide it by V2 in order to cancel that V2 out. But if we divide it on one side, we have to divide it on the other as well. Oops. V2. So now I'm going to clean this up a little bit. If we take P1 times V1 times T2 divided by V2 times T1, that equals P2. That's isolating P2. Okay, and hopefully you tried it on T2 as well. I will bet that at least some of you may have made a mistake on this one. Some of you may have solved for T2 and you got something like this. If you got this answer, I know why you got it, but it's actually not correct. You see, if you solve for T2, remember that T2 is in the denominator. We need to make sure it gets to the numerator if we're going to solve for it. So T2 in this one actually equals T1, P2, V2 over P1, V1. Notice it's the exact, it's the inverse of what you may have gotten before because we need to make sure T2 is in the numerator. Okay, and one more thing before we start dropping in numbers and units. These equations are really important to get before you start throwing in numbers because it's a way of checking your work. But sometimes one of the variables might not change at all. For instance, so here's our little hint. If one condition is not changing, it may be canceled off of both sides of the equation. Let's say that we had a problem and the pressure didn't change. Watch what happens if I erase pressure out of our last equation. It just got rid of P2, just got rid of P1. That equation is actually a legitimate equation for solving for T2 when only temperature and volume are changing. So that's okay. We can actually do that. Also, we're assuming that the amount of gas is not changing. In my little example up here with the boxes, on both sides, N equaled, let's say it's 3 moles because I drew 3 dots. The number of moles is not changing in combined gas law. Also, really big one here. Temperature must be in Kelvin for this equation to work. The pressure and volume, though, they do not need to be. Pressure and volume both don't need to be specific. They just need to be the same on both sides. All right, let's try a couple example problems that deal with combined gas law. A high altitude balloon contains 30 liters of helium gas at 103 kilopascals. Here's one of my suggestions for you. When you're working through these combined gas law problems, let's start labeling things as we go along. We have this balloon. It's our first volume. Call it V1. And we have 103.0 kilopascals. It's our first pressure. Let's call it P1. What is the volume of the balloon? Well, now we have a new volume. Let's call that V2. And we don't know what V2 is. When the balloon rises to a high altitude and the new pressure is 25.0 kilopascals, that would be a new pressure. Call it P2. Also, take note that we're assuming that temperature is constant. All right, now that we have everything labeled, let's start with the equation that is going to get us our answer, the combined gas law. I know that we're using the combined gas law because we have two pressures and we're solving for a second volume. Now, can we get rid of any one of these variables? Yes. If you were thinking we can get rid of temperature because it's constant, you are right. I'm just going to get rid of T1 and T2. This equation, when you get rid of temperature, there's actually a name for this equation. Some of you may have done a video about this one. This is called Boyle's Law. You do not need to know the name of the laws, but just know that they're real. They exist. And in this case, we're solving for the second volume, this one right here. So our next step is to isolate that variable. V2 equals P1 V1 over P2. I think we're ready to plug in our values. As long as our units are the same for pressure, and they're both in kilopascals, we're set. So now let's just plug things in. 103.0. Now, I do want you to include units on this because you're going to make much less mistakes if you include your units. Times 30 liters, all divided by our new pressure of 25 kilopascals. Let me pull up my calculator. I get an answer of, and it's a volume, remember, of 120. I'm going to do sig figs here. It's 3 sig figs, so 124. And the nice part about me showing my units is that the kilopascals cancel out. Notice what we have left for units? Liters, which is a volume. Okay, next problem. Deflategate. This is something real that happened back in, I want to say it was 2017, was it? I think it was the NFC championship between or was it AFC? See, I'm not a football fan. I'm just kind of working off of my recent memory here. Is that the championship to go to the Super Bowl? It was between the Colts and the Giants, and there was this big Deflategate thing where they're wondering, well, the footballs on the it wasn't the Giants, was it? It was the Patriots, right? Because it was Tom Brady. They're saying that the footballs that Tom Brady was using, they weren't up to pressure like they should be. See, the NFL states that footballs need to be inflated to 12.5 to 13.5 psi. It turns out, though, that 11 of the 12 game balls were recorded at 10.6 psi. When asked about this, Tom Brady's response was that, well, these footballs were inflated in the trainer's office where the temperature was 24 degrees Celsius, 75 degrees Fahrenheit, and it was kind of a cold day outside, 10 degrees Celsius, and he said, well, the pressure dropped because the temperature was cold outside, which, as you may remember from our last learning target, makes sense. When temperature drops, particles collide less often. Would that be enough to explain why the pressure dropped to, on average, 10.6? Let's actually solve this one out. You see, without gas laws, we would just have to take people at their word when they talk about, pressure drops this much. Now we can actually calculate out how much pressure the football would drop to if our temperature dropped from 24 to 10 degrees. First, let's start with our equation, the combined gas law. Do we have any variables that are constant? Well, yes. A football has a football has a constant volume. The volume on the football shouldn't change. So I'm actually just going to erase the volume out of this equation. And guess what? This also has a name. Like the last equation was called Boyle's Law, this one is called Gay-Lussac's Law. These laws are named after scientists that did work with gas chemistry. What are we trying to solve for here? We want to know what the final pressure will be of the footballs when the temperature drops. So let's isolate that P2. Now, if you want to work ahead here, go ahead and pause me, and then you can check your answer. P2, once I isolate it, is going to be equal to P1 times T2 all over T1. Let's plug in our values. Oh, actually, let's do one thing before we plug in those values. Do we need to change any of our units? Yes. Remember that, and this is a big one again, temperature must be in Kelvin. It's got to be. If temperature isn't in Kelvin, the equation's not going to work. So do a quick conversion here. What are each of these in Kelvin? Well, we have to add 273. So this one's going to be equal to 283 Kelvin. And this one will be equal to 297 Kelvin. So now let's plug in our values. Pressure 1. What is our initial pressure? Is it 12.5? Is it 13.5? Let's give the Patriots the benefit of the doubt here. Let's assume that they inflated them to the lowest allowable pressure under the game conditions. Let's say in the Turner's office they inflated them to 12.5 psi. Remember that pressure can be in any unit. We just got to make sure it's consistent. Our final temperature outside was 283 Kelvin. They called it a blustery day. It actually wasn't that cold by Minnesota standards. Let's divide that by our initial temperature of 297 Kelvin. And let's do some math. Multiply the top, divide by the bottom. I get an answer of 11.9 psi. What does that mean? Well, it doesn't actually explain why the pressure of the game balls was 10.6. We'd expect the game balls to decrease in pressure to 11.9 given gas chemistry, but it doesn't explain why they were down to the 10.6 psi. Some of you may be thinking, cheater, pumpkin eater. Well, it might be too quick to say that, but at least we can say that the drop in temperature cannot be enough to explain why the pressure dropped to 10.6 in 11 of the 12 game balls. Okay, final one I want to do with you guys here, and then I'm going to give you guys some practice. It says a helium balloon with a volume. Let's just kind of work along here. We got an initial volume, has an original temperature of, let's label that T1, and pressure P1. What is the new volume, as in we don't know what V2 is, at STP? STP. There's that word, or that acronym. Anytime you see STP, remember that we know the temperature and we know the pressure. Do you know the temperature and pressure at STP? Take a second, see if you can remember. I'm going to write it down here, so pause it if you don't want to see. Temperature equals 0 degrees Celsius or 273 Kelvin. And pressure is equal to 1 atmosphere at STP. Okay, let's use our equation and let's solve for V2. We've got our combined gas law, and we're solving for this thing right here. So isolate it. You should try this problem before I finish it off, just to make sure that you're doing things right. Now I have solved for V2 using variables alone. Let's plug in our values and units for each one of these variables. Pressure 1 is 1.1 atmosphere. Volume 1 is 410 milliliters. Temperature 2 is this one here, 273 Kelvin. Now let's divide by temperature 1. Oh, and that is in Celsius. Got to catch ourselves on those ones. If we add 273 to that, that equals 300 Kelvin. And our second pressure is 1 atmosphere. Before I even do the math, let's cancel units. Atmospheres cancels. Kelvin cancels, and we're left with milliliters. So our answer is going to be in units of milliliters, which is good because it's supposed to be a volume. And I get a volume of, oh, I guess I pushed it in wrong. Try that again. No, I guess not. The pressure or the volume doesn't hardly change at all. It's equal to 410.4 milliliters. With sig figs, it's still going to be 2 sig figs, 410 milliliters. Now, why would the volume of this not really change? Well, our temperature doesn't change much at all. It drops by a little bit, and our pressure also drops. So a drop in temperature would suggest that the volume would actually drop. A drop in the pressure around the balloon would result in an increase in the volume of the balloon. So they're actually counteracting, and we end up getting a balloon that hasn't changed in volume at all. Okay, on page 5 here and page 6, I've given you a number of practice problems that I'm going to provide the key for. So try those ones yourself. Page 5, page 6, and also we had those problems on page 3 and on the bottom of page 2. 2, 3, 5, 6. To add on top of that, it's kind of a big week in terms of practice problems. You're going to see that there are 2 sets of problems on Google Classroom that I've assigned. These are quizzes. You can call them a quiz, but really it's practice. And I'd like you to do the first part. That's gas problems part 1, based on combined gas law, what we've worked through here today. I'd like you to complete that by 3 p.m. on Tuesday. As always, I'll be available from 12 to 2 during my office hours.